Okay, so we spent some time in our last lecture talking about boundary conditions for electrostatic problems. And these boundary conditions are, first, the tangential electric field intensity E would be the same across the boundary, as is outlined here. And second, the normal component of the electric flux density D would differ by an amount that is equal to the surface charge density on the surface, which is outlined here. We also talked about what would happen if you have a perfect conductor. And we argued that because there is an abundance of charges freely to move inside a perfect conductor, the electric field inside the conductor has to be zero. And this can be illustrated by this figure here. If you try to establish an external field E1 in this figure, this external field tends to push charges around inside the conductor. And in this case, positive charges would flow towards the top surface and negative charges would flow towards the bottom surface. The effect of this separation of charges is an internal field EI, which acts exactly opposite in direction to the external field. And the separation of charges would not finish until this internal EI exactly balances the external field. In other words, there is no net electric field. So as long as there is net electric field inside, charges would continue to separate until everything balances out. And this has consequences if we relate this discovery to our boundary conditions discussion earlier. So let's look at the boundary conditions in this case. Let's first look at the tangential field. Now, with the electrostatic boundary conditions, we know that the tangential field has to be equal across the boundary. And in this case, my E1t would be equal to E2t. So I'll repeat it here. My E1t would be equal to E2t. Because we just argued that E2t has to be zero because it's inside a perfect conductor, then we know E1t has to be zero as well. This observation tells us that there cannot be any tangential electric field along the surface of a perfect conductor. In other words, all electric fields has to be perpendicular to the surface of a perfect conductor. This is illustrated by this figure where we have a metal sphere inside an electric field. In this case, we assume the metal is perfectly conducting. As you can see, the electric field lines actually bend towards the surface so that all field lines are perpendicular to the surface. As field lines terminate or originate from the metal surface, we know they have to be associated with some charges. When a field line terminates on the surface, we know that there has to be a negative charge there, and when we have a field line coming out of the metal surface, we know there has to be a positive charge there. Now remember that we also have a boundary condition for the normal components of the field. In this case, we know that the difference between the normal components of the electric flux density d1n and d2n would be equal to the surface charge density rho s. We've argued before that d2n has to go to zero because it's inside a perfect conductor. Now we would have d1n equals to rho s. This is a very important conclusion. It tells us that the electric flux density coming out of a perfect conductor would be the same as the surface charge density on that conductor. This conclusion is consistent with Gauss's law. If we take the outer surface of the metal sphere as the Gaussian surface, we can try to verify that the Gauss's law holds here. The left-hand side of the Gauss's law would be d dot ds integrated over this surface, and by this relationship we know this integral would be equal to rho s being integrated over this surface. We know that in a perfect conductor all free charges would be pushed to the boundaries of the conductor if an external field is present, so that this surface integral of rho s would simply give you the total amount of charge or total amount of free charge that exists in this metal sphere. Notice that this is simply the Gauss's law in its integral form. A direct application of the discussions we've had so far is what we call the image method. Sometimes we're concerned with problems in which we have a charge, as is shown here, or certain charge distributions above a ground plane, which is simply a conducting plane. It would be pretty difficult to calculate electric field or electrostatic potential due to this charge, because we haven't learned the necessary tool to deal with conducting objects that are grounded. However, we know that the electric field lines coming out of the charge must be perpendicular to the ground plane, and the field distribution of this problem would be exactly the same as this one, where we have removed the ground plane and have put a negative charge that is a distance d below where the ground plane would be. And because of symmetry, all the field lines in this second case would be exactly perpendicular to this horizontal surface, and the electric field or electrostatic potential would be fairly easy to solve for this second problem, because it would just be a direct application of Coulomb's law. So let's actually solve this problem. We first need to establish our coordinate system for this problem, and in order to be consistent with the original problem, we would call this direction z hat, and this direction x hat, this direction y hat. Obviously, in this coordinate system, the charge q would be at a position of 0, 0, d, and charge minus q, which is the image charge, would be at a position of 0, 0, minus d. The total electric field at point P would be the vector sum of the electric field due to charge q, which we call E1, and the electric field due to charge minus q, which is the image charge, we would call it E2. Complete my drawing here. Now, E1 would be q over 4 pi epsilon times r1 vector over the magnitude of r1 vector raised to the 3 over 2. Now let's look at this r1 vector, which points from q to p, and it's simply the vector difference between OP vector and the OQ vector. So if we were to write out the coordinates for OP and OQ, it would be x hat plus y hat plus z hat for OP, and 0 x hat plus 0 y hat plus d z hat for OQ. And it follows that r1 vector would be x hat plus y hat plus z minus d z hat. And then the magnitude for r1 would simply be the square root of x squared plus y squared plus z minus d squared. Therefore, the E1 vector would be q over 4 pi epsilon times x hat plus y hat plus z minus d z hat, I should have the square bracket, over x squared plus y squared plus z minus d squared raised to 3 over 2. Following a similar procedure, it wouldn't be hard to find out E2 vector, and it would take a similar form. It would be q over 4 pi epsilon. I believe the only difference is the z coordinate, and in this case it would be z plus d z hat over x squared plus y squared plus z plus d squared raised to 3 over 2. The total E field at point P would simply be E1 vector plus E2 vector. So the image method really simplifies the calculation for electrostatic field or electrostatic potential due to charges near conducting planes. To reiterate the process for the image method, for each charge q, you would add an image charge minus q at a position that is symmetrical to the conducting plane. And then you remove the conducting plane and would calculate the field due to all charges using Coulomb's law.